In this video, we'll study the capacitance of capacitors. Capacitors are one of the important components in any electric appliances. The usage of capacitor is very important. In the flash of the camera requires capacitor because it needs more energy, because capacitor stores more electric energy than delivers in a quick time. So it will provide high intensity of light. Another application is we have also the airbags of the car. During accident, it, airbags will be inflated and it uses huge of energy, and it is coming from the capacitor sensor. And there are a lot more of the uh, application of the capacitors. Before we continue studying about this topic, I would like to say thank you to my colleague, Engineer James Lisidan, for sharing his expertise in software. He was able to fix the problem on my laptop and give me the idea on uh, creating videos. So, thank you, sir. Capacitor is a device to store an electric charge consisting one or more pairs of conductors separated by an insulator. So we have these examples are these are the one of the these are the examples of the capacitor. There are we have the cylindrical capacitor, we have the ceramics. Okay? So take note that capacitor contains two conducting metals. These are in the form of plates. Okay, then they are separated with an insulator or maybe a vacuum. Okay, so therefore the two conducting materials have no contact because of the insulator. And this insulator are dielectrics. Dielectrics are materials that has good enhancement of the electric field. Now take note that the two plates have no contact. Now, but if these plates are charged, then it produces electric field. Now, the electric field will be enhanced by the insulator, which are made of dielectrics. The dielectric samples are porcelain, we have ceramic, mica, glass, plastic, etc. Okay, those are dielectric materials. Now, if we connect a supply to the plates where the positive was connected on one plate, the negative terminal was connected to the other plate, then if we introduce voltage, if we switch on the supply, then it stores energy to the plate. The upper plate will receive a positively charged, then the other is a negatively charged. Okay? So, therefore, during the process, the capacitor was being charged until it was fully charged. Because the capacitor has the capacitance value. So, therefore, depending on the uh, physical dimensions of the plate, it requires specific energy, electric energy of that plate. So therefore, for example, in this plate, it was able to receive the 0.55 volts. Okay, so therefore, uh, this this plate was being charged to that voltage, which is 0.55 volts. Okay, so therefore, because we have already the electric charges on the two plates, positive on the upper and we have the negative on the lower plate. So then, the tendency is this will create the electric field. So therefore, it produces electric field because this is positively charged. Take note, in the positive, it is an outward field, while in the negative, it is an inward. So therefore, this capacitor forming actually a parallel plates. So therefore, take note that in our previous video, in the parallel plates, the electric fields are constant between the plates. Okay, so therefore this voltage now reading on the voltmeter or power supply voltage, then this will serve as the potential difference. So therefore, when we see potential difference, this is the potential between the two plates. The higher potential is at the positive, so the upper plate is the potential at A, and the lower plate is the potential at B. So therefore, the potential difference in this example reads 0.55 volts. Okay, so therefore, take note that we had already the supply of energy stored on this capacitor. So therefore, it is now ready to serve electric energy to any load. For example, we want to light up the bulb. Okay, so all you need to do is to connect terminal to the one terminal of the load, then the other should be connected at the other terminal. So you have to connect a line, and then it will light up. Then it consumes energy from the capacitor in a quick time. So therefore, with time, this charge energy at the capacitor will drain because it introduces energy towards this load. So therefore, during the time, our capacitor has already drained of the energy. Okay? So therefore, you need to reach to charge again, then continues the one. So therefore, this is the principle of the capacitor. It receives charge, then it delivers charge. Now take note that the amount of the voltage is not necessary. The voltage that can produce on the capacitor is depend upon the time that the capacitance of the capacitor. So now take note that there are three types of capacitors. We have the parallel plate capacitors, we have the spherical plate capacitors, and we have the cylindrical plate capacitor. Now in this module, we will study the three types of the capacitors and will provide the capacitance value in each capacitor. Okay, so let's start on the parallel plates capacitor. We will provide a relationship on the area, okay, or the charge of the potential difference of the capacitor. So the question is, what is inside of this capacitor? This is a parallel example of parallel plate capacitor. Inside of this capacitor are the two parallel plates and separated by a distance. In between is an insulator or maybe a vacuum. Okay, so this is approximately the materials inside the capacitor. Again, we have these two conducting plates. Then it stores energy that was able to provide the negative charge and the positively charged on its terminal. And take note, it produces electric field. So take note that the positive charge was acquired on some source, okay, and also with the negative charge. The potential difference between this plate is assigned to be B sub EB, means the potential from A to B, from high to low. Now take note, the electric field is constant and it is towards the negative charge at any point. Okay? Now, if you divide this charge, any of this charge, one of this charge, if you divide this charge by the potential difference, the result is capacitance. So we will assign big letter C for capacitance and big letter Q for the charge and B sub EB for the potential difference. Dividing charge by the voltage difference is capacitance value. So the question is, how much is the capacitance value of a parallel plates? What are the parameters that requires of calculating the capacitance? Okay. So first is we will recall that the potential difference of the parallel plates in our previous video is just equal to what? The product of this electric field, which is constant, times D, where D is the distance between plates. So if you multiply electric field with the distance between the plates, the result is the potential difference. Okay? Now, take note, again, recall that the electric field of parallel plates, in our previous video, we provide the example of the parallel plates, is just the what? The surface charge density divided by the permittivity. This is the permittivity of empty space, and this is constant. This is surface charge density. This is the Q per what? This is the Q per area. Okay? So if you divide Q, this Q, any of this Q divided by the area is actually the surface charge density. Which means that if you want to know how much charge of this plate, given the surface charge density, then you have to multiply the surface charge density by area, and the answer is Q. Vice versa, if you want to know how much the surface charge density of this plate, all you need to do is to divide the charge with area. So these are the important things to recall in studying the parallel plates capacitor. Okay? So, going back to this definition, if you divide the charge by the potential difference, okay, dividing the charge by the potential difference, the answer is capacitance. Now, take note that the potential difference, because this is parallel plates, we can substitute it with this value. So, meaning replace this with electric field times D, okay, becomes Q over ED. And our electric field also is constant, remember, and it provides surface charge density divided by permittivity. So replace E with that value. Okay, so now we have Q over the surface charge density divide permittivity, divide also the distance between the plates. Okay, but take note, surface charge density again is Q over A. So replace it, and we have this result. Okay, now we can cancel this charge. So what is now our capacitance value? Our capacitance value is permittivity times A divided by D. Which means that if you want to calculate how much is the capacitance of this parallel plate capacitor, all you need to do is to multiply the constant, the permittivity, with the area. This is the area of the plate. It is the flat area. Okay, it's not the surface. It is a flat area divided by the distance between them. Which means that the capacitance value is directly proportional to the area, and it is inversely proportional to the distance between plates. Okay? So therefore, if you're creating a capacitor, you can always provide the capacitance value of that capacitor. So different dimensions have different capacitor. Okay? Now take note that this should be a conductor. It should be a conductor so that it can store charge. Okay. So this is only for what? This is only for the capacitance for the parallel plates only, because the parallel plates has the area, flat area, and we have the distance between the, meaning other capacitor like spherical, this formula cannot be used. This is intended for parallel plates only. Okay, where? Again, recall that the permittivity is 8.854 times 10 to the 12 coulomb square per meter, Newton meter squared. Okay, and the area A is meter per seconds in unit. Then we have D as the distance between plates. The unit should be M because we are on SI. Then C is the capacitance, and the unit is farad, or simply big letter F. Okay, so therefore the question is, what is the unit? What is the unit of the capacitor? Why is it farad? What is 1 farad? Okay, 1 farad is 1 coulomb per volt. Coulomb per volt, because the definition of capacitance, whose unit is farad, is Q over V, where Q has a unit of charge of coulomb, the charge is a unit of coulomb, and the potential difference has a unit of volt. So therefore, the unit should be coulomb per volt. But 1 coulomb per volt is 1 farad. Okay? Now, this is very important. It is impossible to provide 1 farad capacitance of any capacitor. Meaning, we cannot provide a resistor that has a capacitance value of farad. It is a very big capacitance. Mostly of the capacitance value are microfarad. Okay, we have the millifarad, but farad is impossible to happen. Why? Okay, why is, look at this problem. Suppose we want to construct a parallel plates and we want to have 1 farad. Take note, 1 farad is impossible capacitor. Okay, so suppose we want this 1 farad, and take note that the capacitance is inversely proportional to D. Take note, C is equal to permittivity times A divided by D. So therefore, it is inversely proportional. So you have to reduce the amount of the distance between plates. So let us say 1 mm. 1 mm is a uh, very small distance between the two plates. Now the question is, what will be the area if we want to have the capacitance of 1 farad? Okay, so for the solution, take note of this formula. Okay, we need the area and we need the distance between them in order to solve for the farad, the capacitance. So take note is capacitance is 1 farad and we have this distance between them, then we can solve for A. So manipulating this formula, okay, we want to know how much this area. Okay, suppose our area is square. How much area needed? Okay, so transforming this equation becomes CD over permittivity. Substituting the values 1 farad, then 1 mm per D divided by 8.854 times 10 raised to negative 12. Then the answer is 1.1 times 10 raised to 8 square meter. Okay, so this is the area. This is the area required for a 1 farad. Now, if you want to know how much this length, if it's made up of a square, then you have to take square root of the area. So that this is now the dimensions. The dimensions of your capacitor, if you want to construct the 1 farad, you need 10,488 meters. Okay? Now, the question is, are you willing to construct a capacitor whose dimensions are in square 10,488 meters by 10,488 meters? So therefore, it is impossible. Now take note, the distance between them is 1 mm. Okay? So 1 farad is impossible. It should be in the range of micro, milli, and micro or nano. Okay? So these are the dimensions requirement for that 1 farad. Okay, so if we are now on the way to solve problems on the parallel plate capacitor, okay, take note that we have the area, we have D, we have the charge, and we have the potential difference. We have the electric field. These are the parameters required. So what are the quantities again? The parallel plates. Again, we have the capacitance as the ratio of the charge and potential difference. The unit is farad. We have also the quantity charge. The unit is coulomb. Potential difference, okay, V, volts. Then the area of the plates is A. The unit is meter square. Distance between plates D, the unit is in meter. Okay, so these are the quantities for parallel plates capacitor only. Okay, now what are the formulas? And we have also the electric field E, and then the unit is Newton per coulomb, or an alternative is volt per meter. Okay. Now the formulas are for parallel plates. We can use this. This is the common. This is common to all types of the capacitors. So we can always use this one. C is equal to Q over, which means that if Q is given the problem, divide it by the potential difference. That's it. You are calculating the capacitance. Now another formula is the potential difference. This is intended only for the parallel plates. It is the product of the electric field times the distance. Take note, electric field is constant. So we can simply multiply A by D. The result is potential difference. Then, the electric field, take note again, we did this one in our previous slide. So the electric field again is, for the parallel plates, is just the permittivity, oh no, the surface charge density divided by the permittivity. Okay? Then, take note, the surface charge density for our parallel plates only is Q over A. Then, this is the derived, this is the capacitance, derived capacitance in terms of area and D. It should be the permittivity, A divided by D. These are the important formulas. Meaning, if you are now solving problems in capacitor, all you need to do is to identify all those quantities. Okay, these are the quantities. These are only the quantities required. And after that, since we are already using the given, so what are given in the problem, then find the formula suitable for that. And these are the formulas ready to solve your problem. Okay? So let's start. So for example, we have plates of the parallel plates. Okay? Ano? Problems in the parallel plates. The plates of the parallel plate capacitor in a vacuum are 5 mm apart. So we have the D, no? Because this is unit of millimeters, so therefore, or you can convert this into meter, this is automatically your D. Then, given the area is 2 meter, this is meter square meter in area. So 2 square meter is given. Then we have the potential difference of 10 kilovolt is applied across the capacitor. So therefore, conducting plate A and plate B, okay, so the potential difference is 10 kilovolts. Compute. Letter A, capacitance. Okay, so what is Q? So take note, these are the formula. Okay, so letter B, you're asked to solve for the charge of each plate. And letter C, what is the magnitude of the electric field between the plates? So therefore, all you need to do is to take note what are the given. Given the D, given A, given potential difference. So then you are asked to solve for the capacitance. Now look at the formula. There are two formulas for the capacitance. We have the Q over the potential difference. But the problem of this formula is, okay, we have the potential difference, but we have no Q. Q is actually required in letter B. So therefore, proceed to another formula. This is another formula. C, this is the derived formula for the parallel plates only. The capacitance requires only area and D. So therefore, we can use this formula because area is given as 2 and given the D as 5 mm. So therefore, use that formula for your solution for letter A. Then supply the values. Constant of 8.854 times 10 raised to 12. This is actually the same as a unit of farad per meter. The coulomb square per Newton meter square is the same as the farad per meter. Because take note, okay, we can provide, this is the same as the unit of coulomb square per meter Newton meter square. Then multiply with the area. This is meter already, so consistent. But the 5 mm should be converted to meter. So you have to raise it by negative 3 because negative 3 exponent is for meter. Okay. So then calculate the value. The result is 5.4 times 10 raised to negative 9. Okay. So then it is equivalent to 0.00354 microfarad. Okay, so then letter B, you are asked to solve for the charge. Okay, now since we have already this capacitance, then we can use the definition of the general definition of the capacitor, the Q over the potential difference. So take the general product of that, solving for Q, it is the capacitance times the potential difference. The capacitance is 3.54 times 10 raised to 9, and the potential difference is 10 kilovolts converted to volts, multiplied by 10 raised to 3. So 10 raised to 4, okay, wait. This is 10,000 kilovolts. 1 times 10 raised to 4 is volts already. So therefore, this volt can be cancelled out, unit. So therefore, leaving the charge of C. So the answer is 3.54 times 10 raised to 5 coulomb. This is the answer for letter B. Letter B, you are asked to solve for the magnitude of the electric field. Take note, there are two formulas. Okay. Now, the formula for the electric field is, take note that the potential difference is electric field times D in our previous slide. So therefore, and another formula is the surface charge density over permittivity. Okay, but take note that surface charge density is Q over A. So therefore, we can utilize this formula. So therefore, replace this one with Q, and the area is this 2. Permittivity is constant, so therefore, calculate, and the answer is 2 times 10 raised to 6 Newton per coulomb. Okay, so therefore, these are the answers to the problem. Again, there is another way to solve for E. Take note. You can use the potential difference, okay, this one, so 10, then divide it by D. You will arrive the same answer, 2 times 10 raised to 6 Newton per coulomb. You can do it. Okay. So, okay, look at this one. This one is what? This is the potential difference formula. Electric field times this. So meaning, if you divide both sides by the solving for A, this is the potential difference divided by D. So you can use this relation to recalculate again letter C, then you will arrive the same answer. Okay? So, that's it for the parallel capacitor. Now, what will happen if our capacitor is spherical? Okay? So, if we have spherical, so therefore, it should be like a ball. Okay? So, suppose we have a ball inside, but it is hollow. Okay? It is hollow spherical. You can imagine a ball, okay? Then inside is air. Basketball, inside is air. So, it is actually a hollow sphere. It is not a solid sphere. Now, the hollow sphere was charged with a positively charged, okay, at the surface, because the charge stays at the surface only. Now, we need to enclose that with another hollow spherical object, and it was now charged by negatively charged. So if you are forming this kind of setup, then you are creating a kind of spherical capacitor. Okay, again, we have a sphere, hollow sphere, with a charge of positive. Then we enclose that positive charge hollow sphere with another hollow sphere. Okay, but it was now charged with a negatively charged. So this is now, if the spheres are conductor, then we can call this as a spherical capacitor. So if you cut this one, okay, the positive, this is a hollow part, and at the surface is positively charged. Then the negatively charged is the outer part or outer spherical. Then this will be the cross-sectional appearance of that. So this is a hollow part. Then, okay, we can provide the dielectric between these two, but this one is a hollow space. So then, this is a negatively charged, the outer part. Now, this is spherical capacitor. So therefore, we need to provide that radius. It is required to measure that one. Radius, RA is the radius of the positive hollow cylinder, hollow spherical charge. Then RB is our radius of the outer spherical conductor. Okay? So, the question now is, what is the capacitance value of this capacitor? Now, take note, this is a general formula. So, if the capacitance of the the parallel plates is permittivity times A, area divided by D. The question now is for spherical, what is now the capacitance value? So we will utilize the radius of the positive conductor and the radius of the negative conductor. So therefore, C should be expressed in this value. Okay. Now, take note that in order to provide capacitance, we need charge. So this is the charge. Any of these two, we can put it here. Now, next is we are required to know how much is the potential difference between A and B. Now, in this case, this is our A and this is our B. So therefore, we need to calculate the potential at A. Okay, we need to calculate the potential of A and potential of B, because if you take the potential difference, the answer is the potential difference from A to B. So therefore we need to calculate how much is the potential at A and how much is the potential at B. Okay, so how? Okay, now take note that this is not a solid. This is we cannot. This is not a point charge. Okay, so therefore the question is, what will be the potential for a hollow sphere? Okay, now recall first. Now take note, in a solid sphere, this is a solid sphere whose radius is R. Okay, solid means everything was occupied by the metal. But take note, if you say that this is a positively charged, remember that the charge stays only at the outer part of that, or the surface of that sphere. So therefore, if you are asked how much is the potential at that point, let us say at R, then to answer, this is basic on our definition of potential difference. Review our previous video. So to answer this one is simply 1 over 4 pi permittivity, the charge divided by R. Okay, that's it. Because this is solid sphere. Now our problem is what? It is a hollow sphere. So therefore, this is the real situations of our problem. We have this positively charged and we have this a hollow sphere. This is unlike this one because it's a solid, but this one is hollow sphere. The question is, what if you are asked to solve for the potential difference at this point, which is outside of the surface? Whose radius is R? The same R, the same radius. Now, let us say the same R. What will be R? What will be the potential difference at that point? Okay, the answer is the same. Why? Why? Okay, now take note. Even though this is hollow, the two are treated to be the same. Why? Because again, remember that the charge stays at the surface only. So therefore, in a solid sphere, the charge stay at the surface, and also the hollow stay at the surface. So therefore, there is no difference of the two if you are calculating the potential difference. Meaning, we can treat this as a point charge. Okay? The reason is because the charge have the same location for the solid sphere for the same radius, because it stays on the surface only. So therefore, we can treat the hollow as a solid sphere, or we can use the principle of finding the potential of a point charge particle. This is again a point charge particle formula. And if you notice that for continuous charges have different potential. Now this one, we cannot classify this as uncontinuous. Why? Because this can be treated as a point charge. So therefore, simply use this formula. So the potential at the surface of a positively charged is equivalent to 1 over 4 pi permittivity Q over RA, while in the outer sphere, which has a charge of negative Q, has the 1 over 4 pi permittivity Q over RB. Okay? So, these are the two potentials. The two potentials. The potential at A and the potential at B. So, therefore, replacing it here, because we need the potential difference. Remember, we need the potential difference in order to solve for the capacitance. So, therefore, we need to substitute the potential at A subtracted by the potential at B. So therefore, this is the result. Okay. Now take note, we have common here. We have common charge and we have the common constant. So we take out the common and we have Q over 4 pi permittivity, quantity 1 over RA minus 1 over RB. Okay, so therefore, take note, this is the, by the way, we have to combine the two fractions, take the LCD, then we come up with RB minus RA divided by RA times RB. So therefore, this is the potential difference in terms of the charge and the two radius. Okay, so we are now ready to solve for the capacitance because we have this Q substituted here and we have this potential difference here. So then, take note that we can cancel Q, okay, and transforming this one will gives us 4 pi permittivity quantity R times A times RA times RB divided by RB minus RA. This is the capacitance of spherical plates. This is for spherical plates only. Again, take note, remember that the parallel plates is C is equal to permittivity A divided by D. But this one, this is in terms of the radius of the sphere. Okay, so therefore, we can always find the capacitance value of the spherical provided radius are given. So take note that we don't need the charge in order to to know how much is the capacitance of that capacitor. We need only R because these are constants. The radius of the positive charge sphere and the radius of the negatively charged sphere are the requirements in order to solve for the capacitance. Now for cylindrical, this is cylindrical, sorry. This should be cylindrical surface. This is cylindrical, okay. Cylindrical. This is cylindrical capacitor. So, suppose given the charge of the cylindrical capacitor. Take note, this is a hollow cylinder also. It can be hollow or okay or a solid. You can do it. So then we have this surface charge density given as the linear charge density positive, okay, whose radius is RA, okay. Then we will enclose this with another cylinder, but this time it should be hollow cylinder, whose radius is RB. RB is coming from the center towards the outer diameter, okay, or surface. So therefore, this is a kind of cylindrical cylinder, okay. So because we have two charges, take note that whatever charge here, the same charge here. Then this is expressed in terms of linear charge density. Okay, so then suppose, take note that if this is charged, these are charged with the two conductors, then we can provide always the electric field. The red arrows represents the electric field. Okay, so suppose we have this length of the cylinder. So then we can say that the linear charge density is just Q over L. Now take note that not necessarily L is given. Okay, suppose we know. So that we want to have the value of Q later. So therefore, your linear charge density is Q over L. Now this we have to recall again the electric potential for infinite cylinder. So if you have not been watching for the video for the previous potential, electric potential, so you're encouraged to watch first the video before going to study this video, because we need to recall the electric potential for infinite cylinder. So the conducting cylinder or the infinite line, the electric potential for infinite line or conducting cylinder in our previous video says that the potential difference of the infinite line cylinder or conducting cylinder, then this is equivalent to the linear charge density divided by 2 pi permittivity, then the natural logarithm of R times R naught, where R is the distance from the center outside the surface, and this R naught is the radius of the circle, okay, or the cylinder. Now take note that this is where that the potential is zero, and remember that the potential at the surface of the cylinder is zero. So therefore, okay, but this one R naught now becomes R in our case. So therefore, this is RA, okay, which is the radius of the inner part, and your RB is your radius of your outer cylinder. So therefore, this is the potential difference for the cylindrical capacitor. Okay? If you are asked to calculate what is the potential difference, then use this formula. So therefore, going back to the general formula for the capacitance, Q over the potential difference, we have now the potential difference for the cylinder. So all you need to do is to substitute. Okay? Now nothing can be cancelled. We can cancel Q. So that's why we need to replace the linear charge density and express that in terms of Q. So therefore, this will becomes Q over L. So we can now cancel Q. This is Q over L is the linear charge density. So cancel Q, leaving this result. Okay. So this is now in the denominator position, while our numerator, while this one is the denominator. So this is the capacitance of the cylindrical capacitor. Now take note, this is if L is given. Okay? But if L is not given, you can divide this and say it capacitance per length. So the capacitance per length is 2 pi permittivity over the natural logarithm, the absolute value of the RB over RA. So this is the capacitance of cylindrical capacitor. We have the capacitance in terms of L, and we can express that per length of this, which means that again we can compute the capacitance per length if R are given. If the radius of the inner cylinder and the radius of the outer cylinder are given, then we can always calculate the capacitance per length of that. Okay, so this is it. The three capacitor: the parallel capacitor, the spherical capacitor, and we have this last, the cylindrical capacitor. Okay, so for your practice, try this. This is on just the parallel plates capacitor. Okay, we don't have problem for the other capacitors. So for in this video, try this. Okay, thank you.